In this video, we discuss the idea of a smooth parameterization. We say that a parameterization is smooth if the following is true. So we're going to say we have a vector valued function r of t. It generates a curve. And that curve C could live in 2 dimensions or 3 dimensions or n dimensions, and any of that would be fine. But when I look at the curve C, I'm going to say that it's smooth if it looks like this. So as t increases, maybe our curve looks like this. No sharp corners. Now, if the curve does have sharp corners, like maybe it looks like this. I've got a sharp corner here and here, and maybe at some point just decides to be a straight line for a while. Curves don't decide, but you know what I mean. That would also be a sharp corner. This is not smooth. But we might say that it's piecewise smooth. Because even though it does have those 3 sharp corners, it is smooth in pieces. Like this initial piece is smooth, and then all of this is nice and smooth. It's fine until I get here, and then I've got another smooth piece, and then I've got another smooth piece. So this is piecewise smooth, or smooth in pieces. And that's exactly what we would see. If you've got sharp corners, it's not smooth. If you have no sharp corners, it's smooth. But often, if we do have sharp corners, we can still at least think of it as piecewise smooth. But we have to keep that in mind when we need a smooth parameterization. So you say, okay, well, what does that have to do with r of t? Well, here's the algebraic definition of smooth. This is the idea that we're talking about. You might say, if you give me a formula r of t, how do I know when it's smooth? Well, here's your algebraic way of looking at smoothness. If r is a parameterization of c, and let's just say that we're in 3 dimensions, but this works just as well in 2 dimensions or n dimensions. It's fine. So r has some parametric equations, x, y, and z. If r is given by this, and the component functions, its component functions, are continuous, and r prime is not the 0 vector, for all t in some interval. I'm just going to call that I for interval, all t in some interval I. Then we call r a smooth parameterization. And the curve that is generated by r is probably going to look like this. You might say, well, what does all this mean that we've said? We said the component functions, in this case if we're in 3D, x of t, y of t, and z of t, all have to be continuous. And r prime of t cannot be 0. Let's think about what r prime of t being the 0 vector means. R prime of t is the vector with components x prime, y prime, and z prime if we're in 3D. And we're saying that cannot equal the 0 vector. So this would be a problem. We'll have an issue if x prime, y prime, and z prime are 0, but get this, they have to be 0 at the same time. If they're all 0 at the same time, you might be looking at something that looks like this. You might have a sharp corner here, or a sharp corner here, or a sharp corner there. So we're saying this can't be 0, Or alternatively, x prime, y prime, and z prime cannot be 0. I don't know why I put this there. At the same time. It's okay if one of them is 0 and the other ones aren't. But if all three are 0, all bets are off. We might have a sharp corner. Okay, so let's look at a curve and try to find the time intervals when the curve, or when the parametric curve is smooth. So this is r of t. It has components 5 cosine of t minus cosine of 5t and 5 sine of t minus sine of 5t. And we're given an interval. We're told that t is between 0 and 2 pi, including the endpoints. And the question says, on what intervals is r of t smooth? Okay, let's figure that out. Well, in order to do that, I don't know what it looks like yet. It's actually one that's a little bit hard to figure out what it looks like. I want to compute r prime, and I want to see when all the components of r prime are 0 at the same time. And those are going to be the t values that are a problem. Now we're not looking for all of the possible values of t where r prime is 0. We're looking for the values of t on the interval from 0 to 2 pi that cause a problem. So let's find r prime and then think about when on this time interval we might have this 0, 0 problem. Since we're in 2D, it's just going to be 0, 0 instead of 0, 0, 0. So this is our x component. This is our y component. So r prime is just given by x prime, y prime, x prime times I hat plus y prime times j hat. So we're taking the derivative of 5 cosine of t minus cosine of 5t, and we'll take the derivative of 5 sine of t minus sine of 5t. Okay. Bring down your 5. The derivative of cosine of t is negative sine of t. Bring down your negative 1. Now when you take the derivative of cosine of 5t, you've got to use the chain rule, because we've got an inside function here. Derivative of cosine of a function is negative sine. Negative times negative is going to make that a positive. Sine of that function, 5t, times the derivative of the inside by the chain rule. Derivative of 5t is 5, so we get a 5 right there. Similarly, you bring the 5 down. Derivative of sine of t from calc 1, that's cosine of t. Derivative of sine of 5t, bring the negative down, is cosine of 5t. Put the inside function back in. So you got to use the chain rule again. And the derivative of the inside is a 5. All right, so now I want to know when this is 0. When I say 0, I mean the 0 vector. When are both of these 0 at the same time? So what I really have is a system of equations. There's only one unknown, it's t. So x prime is, I'm going to write it in a different order. I'll put 5 sine of 5t first, and then we're subtracting 5 sine of t. And y prime is 5 cosine of t minus 5 cosine of 5t. And I want to know when both of those are equal to 0 at the same time. Well, with each of these equations, just ignoring that part, I've got 5 multiplying everything. It's unnecessary. So we can divide everything by 5. We've got sine of 5t minus sine of t here equals 0. And simultaneously, cosine of t minus cosine of 5t equals 0. Now this is a hard system of equations to solve. I think sometimes it's obvious when t equals 0, sine of 0 minus sine of 0 is going to be 0. When t equals 0 here, cosine of 0 minus cosine of 0, regardless of what cosine is, right? Regardless of what cosine of 0 is, right? We're going to have cosine of 0 minus itself, it's 0. In that case, it's 1 minus 1, which is 0. But that's only one value. We know the same thing's going to happen at 2 pi. So we want to solve this for all possible values of t that lie in the interval that we were given. In order to do that, I'm going to get some trig identities out. Now, this is actually one I had to look up myself, because this is not something that I even remember after teaching all of these years of math. This is sine of an angle minus sine of a different angle. So I've got these sum to product formulas. I've got sine of u minus sine of v. So this is my u, and oops, this t is my v. And then I've got a formula for cosine of u minus cosine of v. So u is t on this one, and v is 5t on that one. And we want to use these formulas with these equations to make them a little bit easier to solve. Because if I have a product equals 0, it's much easier to figure out the values of the angles inside that would give me a 0 than if I have this difference. So using this top identity for sine of 5t minus sine of t, five t is my u, t is my v, I'm folding the piece of paper so that we can see it on the screen. Okay, so I've got this right here. According to the identity, I get 2 times cosine of the sum of the two angles divided by 2. So I've got 5t plus t up here. And then next to it, multiplying it, I've got sine of the difference of the two angles divided by 2. So I've got 5t minus t there. And of course we can simplify those and then set them equal to 0 and then solve for the possible values of t. Okay. So I'm right here now. Sorry guys. Got 2 times cosine, 6t divided by 2 is 3t, times sine of 5t minus t is 4t, 4t divided by 2 is 2t, and that's equal to 0. Now the only way that product is 0 is if one of the factors is 0. So that means either cosine of 3t is 0 or sine of 2t is 0. And you might have to go back to trig, remember, when is cosine 0? When is sine 0? So I'm going to draw some curves. Now I'm not going to plug in the 3t or the 2t, I'm just going to look at cosine of theta at sine of theta. Cosine of theta looks like this. It repeats every 2 pi. It starts at its max of 1. And then all the interesting things happen at 1/4 of the period. So 1/4 of the period is pi over 2. Then we're at pi, then we're at 3 pi over 2, and then we're at 2 pi. Those are our special angles if we look at our unit circle. So we're on the x-axis, that's theta equals 0, then pi over 2, then pi, then 3 pi over 2, and then 2 pi. But we're not going to look at the unit circle. Instead, we're going to let this be the angle that's going around the unit circle. And cosine starts at its max, and then it goes to 0, then it goes to its min, then it goes back to 0, then it goes back to its max, and it keeps repeating. And y equals sine of theta looks similar, but it doesn't start at its max, it starts at 0. All the interesting things happen here at 1/4 of the period. And it oscillates between -1 and 1 as well. So it starts at 0, then it goes to its max, then it goes back to 0, then to its min, and then to 0. So we're here. Okay? All right. So I need all the values of t between 0 and 2 pi that give me a cosine of 0. Well, according to this picture, cosine of 3t will equal 0 every time 3t is an odd multiple of pi over 2. So when 3t is pi over 2, we'll get 0. When 3t is 3 pi over 2, we'll get 0. And if I solve those for t, I get t is pi over 6, and this one I get t is pi over 2. You might say, are there more? Well, let's see. The next time 3t would be 0 is at 5 pi over 2. Because cosine of any odd multiple of pi over 2 is going to give me 0. I have pi over 2, 3 pi over 2, the next one will be 5 pi over 2, then 7 pi over 2, and so on. You're going to keep going. I need to keep going with all those angles until I get a t value that's greater than 2 pi. Then that's outside of the interval that I'm interested in. So I'm not going to worry about that guy. Let's take this one and divide by 3. So we're going to get 5 pi over 6. Remember, dividing by 3 is multiplying by 1/3. So I'm just doing 1 over 3 times this, and the 2 times 3 is giving me the 6. Say, okay, well that's still within 0 and 2 pi. So keep going. Do 7 pi over 2. Let's do 9 pi over 2. And 11 pi over 2. And 13 pi over 2. Okay. So we divide by 3 and we get this. Divide by 3 here. You divide by 3 on this one, you get 3 pi over 2 because the 9 is divisible by the 3. This one, you get this. And then look what happens here. You get that. But 13 pi over 6, that's more than 2 pi, so we're not interested in that guy. Notice we got 6 answers. 1, 2, 3, 4, 5, 6. You might say, how did, is there a pattern there? Could I have predicted that I got 6 answers from that one? That's a great question for trig class. But yes, we can predict that we get 6 answers. And you say, how do you know? Well, if I replace the t with a 3t, that means instead of having one wave that looks like this between 0 and 2 pi, we're going to have 3 waves for cosine of 3t. It's actually going to do that thing 3 times. And it's hard to draw on there and make it perfect, so I'm not going to draw it on there. But basically, it's going to go from max to min to max 3 times, from 0 to 2 pi. So that means if this is 0 twice, if this one wave is 0 twice on the original period, if I'm going through that period 3 times as fast, I'm doing that 3 times instead of once, well, the first time I'm going to get these guys, the second time I'm going to get these guys, and the third time I'm going to get these guys. So since I had 2 zeros here, 2 t values that gave me a 0 here, and we're going 3 times as fast, I expect to get 6. 2 times the 3. I'll get 2 t values for each wave, each time that wave goes through the t axis. Okay, something similar is happening here. Sine of 2t is going to equal 0. Whenever 2t is following this pattern, notice sine is 0 at 0, pi, 2 pi. The next one would be 3 pi, 4 pi, 5 pi. Or we go backwards, negative pi, negative 2 pi, negative 3 pi. So anytime we've got a multiple of pi over here, we're going to get 0. So I want to know, when is 2t equal to a multiple of pi? Notice we're going to get 3 answers here, but some of them are on the end, so that makes things a little wonky, to make counting our solutions a little harder. But let's just stick to these ones. So we'll say 2t equals 0. That means t equals 0. When 2t equals pi, we get t equals pi over 2. When 2t equals 3 pi, we get t equals 3 pi over 2. 2t equals 4 pi, that means t equals 2 pi. And then we don't want to go any further. So we just get 4 solutions this time. Okay, that's a lot. All we did there was see when x prime would equal 0. So x prime is equal to 0 at all these t values and all these t values. I want to know, when is y prime also equal to 0? So let's look at our y prime. Y prime looked like this. It was cosine of t minus cosine of 5t. And we've got an identity for that. So u in our case is t. This is our u. And v in our case is 5t. So according to this identity, I get -2 times sine of the sum of the two angles divided by 2. So it's a t plus a 5t. Times another sine of the difference of the two angles divided by 2. T minus 5t is right here. So this is -2 sine of 6t over 2 is 3t. Here I've got -4t over 2. That's -2t. Now you can leave it like this if you want to, but here's another fact. It's another identity. Sine is an odd function. When I say odd, I don't mean it's strange. I mean sine of t and sine of -t are closely related. If I look at them on the graph, here's sine of t, or yeah, just a sine wave. If I go t units in this direction and I find the y value, and I go t units in the opposite direction and find the y value, those y's have the same magnitude but opposite signs. So if I went to say pi over 2 for t, well, the y value is 1 over here, so that's sine of t. If I go pi over 2 units this way, so I'm looking at sine of -pi over 2, I get a -1. So these two y values have the same magnitude but opposite signs. So sine of -t is actually -1 times sine of t. So this y value is the opposite of that y value. With that in mind, this negative, it's not factoring. It looks like factoring, but it's not factoring. I can pull that negative out, and I can say that this is equal to this. And we want to know, well, when is that 0? So you're going to set that equal to 0, and you're going to solve for t. And then we solve a trig question, solve a trig equation. It's probably been a while. Nice little review. Got sine of 3t and sine of 2t. And that is 0. The only way that's 0 is if one of these factors is 0. So either sine of 3t is 0 or sine of 2t is 0. And we can look at our sine waves again. Sine is 0 at all the multiples of pi. 0 pi, 1 pi, 2 pi, 3 pi, negative pi, -2 pi, -3 pi, and so on. So we're going to get 0 when 3t equals 0, so that means t equals 0. When 3t equals pi, that means t equals pi over 3. 3t equals 2 pi. I'm just setting 3t equal to all the multiples of pi. So we get 2 pi over 3. And you want to keep doing this until you get to a t value that's beyond 2 pi. Because remember, we were restricted. We were told that t lies between 0 and 2 pi. So we get this t equals pi, and I think we're just going to get 4 more like that. Just seeing the pattern that we got 4 in the first pi radians. We have 4 pi, 5 pi, 6 pi. Actually, I know I'm going to solve that one, and I'm going to get t equals 2 pi. So we're done. So this is 4 pi over 3, and this is 5 pi over 3. Okay, so that's for that one. And sine of 2t equals 0, we actually found those values already up there. So just based on what we did before, we got 0, pi over 2, 3 pi over 2, and 2 pi. Okay. Now these are the t values that make y prime equal to 0. I need x prime and y prime to be 0 at the same time. So I look at these lists and I see what the two lists have in common. Is pi over 6 on both lists? It's not. I've got a bunch of multiples of pi over 6 here. None of them reduce to nice multiples of pi over 3. There's no simplification like that. And I've got multiples of pi over 3 here. So I can rule that out. I don't have pi's over 6 and pi's over 3, multiples of those in both answers. So none of those solve the simultaneous system of equations, x prime equals 0 and y prime equals 0 at the same time. So that's not it. That's not it. That's not it. And that's not it. Anything with a 6 in the denominator is not going to work. Anything with a 3 in the denominator is not going to work. Okay. Is pi over 2 on both lists? Pi over 2 works here and here, so yes. And I also skipped one. What about 0? Is that on both lists? Yes. Actually, all of these guys are on both lists, so let's write those down. Because we had that sign of 2t equals 0 for both equations. Okay, so those are good. Now let's look at these lists. Pi over 2, we actually already covered that. 3 pi over 2, we have already covered that. 0's on both lists, pi isn't. 2 pi isn't. Oh wait, yes, 2 pi was on both lists. Is that right? Did I get a pi over here? No, I think actually I should have had a pi here. Somehow I skipped this one. 2t equals 2 pi, so t equals pi. Alright, let's add that to the list. I'm just putting it in there because it's in between those two angles. Okay, so that should have been on there. Sorry about that, guys. Somehow, I don't know why, but I skipped that one. Alright, so we have 5 answers. At 0 pi, or 0 pi over 2, pi, 3 pi over 2, and 2 pi. These are both 0. So at these t values, the curve r of t, or the curve generated by r of t, is not smooth. Or we say that r of t is not a smooth parameterization. I'm not going to prove this to you right now, but I think it's kind of cool. I saw this in a textbook. It's a different textbook than the one we use in our class. But let me show you what this looks like. I just think it's pretty. R of t had these components: 5 cosine of t minus cosine of 5t, and 5 sine of t minus sine of 5t. It turns out it looks like this, sort of 4-leaf clover-ish. And as t increases, you go this way. Isn't that pretty? I think it's pretty. See where all those sharp corners are? At 0, at pi over 2, at pi, 3 pi over 2, and 2 pi is the same as 0 when we look at those angles. So that is what r of t looks like, and you see it's nice and smooth everywhere else. But we've got these little corners, and that's a little bit of a problem. So that's smoothness, guys. You are looking for the t values that make both of these 0 at the same time. Often, they're not both 0 at the same time. So let me show you one that's smooth all the time, or smooth on its entire domain. This one's actually really easy. Let's say you want to prove it. Let's look at r of t with components t and t squared. X equals t, y equals t squared. So if you put those two together, you replace this t with an x, you get y equals x squared. We've seen this one before, it's just a parabola. As t increases, x increases, so it looks like that. If I want to find the intervals where this is smooth, first I need to compute r prime, and I get 1 and 2t. Question is that ever equal to the 0 vector? Am I ever going to get a 0, 0 out of this? I hope you said no. The system of equations that we would have here is x prime equals 1, which equals 0, and y prime equals 2t, which equals 0. 1 is never equal to 0, guys. So there's no problem t-values. We'd only have an issue when t is equal, or when we have a t-value that we can plug into this and get a 0, 0 out. And we're never getting a 0, 0 out of this. So this r of t, or r prime of t, is never equal to the 0 vector for any t in the domain, and the domain it happens to be all real numbers. So the parameterization is smooth all the time. And we can look at our curve, and we look at our parabola, and we know it's smooth. Most of the time, this is what you're looking at. It's it's hard to even write equations that can make x prime and y prime both 0 at the same time. If there's a case where, this one I can set equal to 0, t equals 0, well then, if this is 0 and t equals 0, I'd need to check to make sure that x prime is also 0 at that time. And if this is 0 and t equals 0, but this one's not, or any of the other ones aren't, then that t value is not a problem. The function is smooth there. Or the vector valued function, the parameterization is smooth there. And what that means for our picture is that there's no sharp corners. So this is much more like what you would see. I just thought that this was a beautiful, interesting example. You're not likely to see anything like this on a quiz, but I didn't want to tell you until after you watched the video.